Hello students, in this video I am going to explain the concept of radio frequency transmission line. The learning objectives for this video is students should be able to define transit time, students should be able to compare lumped and distributed components, they should be able to draw the lumped equivalent of transmission line, and they should be able to define the transmission line parameters. So let us start with what is RF. RF stands for radio frequency, and a frequency or a band of frequencies in the range of 10 raised to 4 to 10 raised to 11 or 12 hertz is called as a radio frequency. So the frequency band is from 10 kilohertz to thousands of gigahertz, and it is more suitable for telecommunication. So let us understand the properties of RF current. Radio frequency current has tremendous energy in it, and therefore this energy can radiate off the conductor into the space in the form of electromagnetic waves, which we also call as radio waves. Electromagnetic waves are self-propagating waves, oscillating waves having electric and magnetic fields which are transverse to each other, that is perpendicular to each other. If such RF current is carried by a ordinary electric cable or wire, then it has a tendency to reflect from the discontinuities in the cable, and therefore it can travel back to the source, and therefore RF current must be carried by a specialized type of cables called as transmission line. So what is transmission line? Transmission line is a specialized cable or a structure which is used to carry alternating current or a radio frequency from source to load. So as in the diagram you can see a source which is connected to load, okay, through this transmission line, which is nothing but the coaxial cable. So coaxial cable is one of the type of transmission line having two conductors, inner and outer. So these are the common types of transmission line which is used: two wire lines, coaxial cables and microstrip lines. So now let us understand the concept of transit time, lump component and distributed components. For that, let us consider a current having a length of 5 cm. Now let us consider that this conductor has a resistance R ohm, and we can apply Ohm's law, which is V is equal to IR, that is applicable. Now let us assume that this conductor is connected to a source which produces a signal of 50 hertz. So now this conductor is carrying that signal. So what will be lambda? What is lambda? Lambda is the wavelength, which is a length of one cycle of this signal. So lambda, if I substitute it, which is equal to C by F, C is 3 into 10 raised to 8, that is speed of light. If I substitute the values, I get lambda as 6000 km. That means this distance of 50 hertz frequency is 6000 kilometers. So therefore at low frequency, 50 hertz is comparatively low frequency, we can say that the signal length or wavelength is far more than the component length. So 6000 kilometers is far greater than 5 cm, and we can say that the voltage and current signals are independent of the space. That means the voltage and current magnitudes at one end of the conductor is same as at the another end of the conductor. We also can assume that the resistance is concentrated at a single point in the space. That means the resistance value can be assumed to be concentrated at a point over the length of the conductor. Such components are called as lump components, wherein the effect can be assumed to be concentrated at a point. And when we apply KVL or KCL, we get a differential equations for such components, and transit time is negligible. What is transit time, we will see later. So therefore we can say that at low frequency circuit components are lumped, wherein the current and voltage at all points are of same value, and the examples are resistor, inductor and capacitor. Now let us see a different scenario. So what is the difference is, now the source of 4 gigahertz, that is the RF frequency source, is connected to the conductor. So now this conductor is carrying a signal having a frequency which is 4 gigahertz, and it is having the same length. Now if I calculate the lambda value, then I get lambda value as 7.5 centimeter, which is comparable to the component length. So 7.5 centimeter is comparable to 5 centimeter. So here voltage and current of the signal is dependent of the space, that is voltage and current at one end of the conductor is different than what is at the another end of the conductor, so they are dependent on the spatial coordinates. So such components are called as distributed components. So resistance, inductance, capacitance, they are distributed over the length of the component, and therefore if I apply KVL or KCL, then I am going to get a partial differentiation, because now this voltage and current is not only dependent on time, but it also depends on the spatial coordinates. And in this case the transit time is significant, therefore we can say that at high frequency the circuit components are distributed because voltage and currents at all points are of different value, and the example of distributed component is a transmission line. So transit time can be easily understood by this picture, wherein I have assumed a bigger vehicle that is of low frequency having the bigger wavelength, which we have seen earlier as 6000 kilometers, and this small vehicle is of a higher frequency of a small wavelength that is of 7.5 centimeter, and if it is to be traveling on the road which is on the transmission line, then it is very clear that this is high frequency signal and the propagation time is significant, that is the time taken from this vehicle to travel from one end to the another end of the transmission line, it will take some time, whereas for a low frequency signal it will take hardly any time to reach to the another end of the conductor. So transit time is negligible for low frequency and it is significant for high frequency. So therefore we have seen that the circuit components R, L, C and G are not concentrated at a point, but they are distributed. So therefore if you want to understand such systems, then we need to convert it into a lump circuit. So therefore we divide our transmission line into small sections, so that over that small section the transit time is negligible, so that we can do a lump circuit analysis of this small section. So let us assume a transmission line and I divide it into a small section. Let's assume that this is a small section of transmission line of the length delta Z. Now delta Z is assumed because I assume that the transmission lines is laid on the Z axis. So therefore I have assumed this small section of a transmission line and such that delta Z is far less than lambda, and now I am going to write down the equations for it. So let us assume the small length of the transmission line. Now here current and voltages are depending on time as well as spatial coordinates, and its lumped component can be drawn like this. So the voltage at one end of the transmission line is V and another end of the transmission line is V plus delta V. Similarly for current I at one end and I plus delta I on another end, and this resistance, inductors and capacitor and conductance are the four parameters per unit length. So these are the four per unit length parameters of the lumped equivalent. So now I have to apply I have to write down the equations. So once I apply this voltage, alternating voltage source to the transmission line, I am going to get the current. As this current passes through the series components, and some part will be traveling through this parallel component, and therefore the current at this another end will be different. Let's assume that its current is I plus delta I. Similarly, there will be some voltage drop in the series component, therefore voltage at one end will be different than voltage at the other end. Let's assume this voltage as V plus delta V. So therefore the voltage drops can be written by the equation as delta V is going to be minus R delta Z into current plus L delta Z into current. L is written as j omega L, that is XL value. Similarly, the amount of current which is passing through these two parallel components is going to be the admittance into voltage. So the admittance is going to be G delta Z plus j omega C delta Z, that is admittance into voltage. So these are the two equations which I get. In the same equations, the delta Z is taken common from both the equations, and now I'm going to take this delta z to the denominator here. So delta v upon delta z is equal to minus r plus j omega L into I, and delta I upon delta z is equal to minus g plus j omega c v. Now I'm going to take the limits wherein delta z tends to 0. Now the reason why I'm taking a limit is that we have assumed that over that small section of the transmission line the transit time is negligible, but at some frequency, at a higher frequencies, still even that small section there are possibilities that the transit time is significant. So therefore, in order that the transit time is negligible for all the frequencies, I am going to take this limit wherein delta z tends to 0, and therefore I get the equation as dv by dz is equal to minus r plus j omega L into I. Similarly, limit of delta z tends to 0 of delta I by delta z is di by dz is equal to minus g plus j omega cv. Let's go further. So now I'm going to differentiate the previous equations on both the sides. So I get here d square v by dz square is equal to minus r plus j omega L being constant, di by dz, and even the second equations is differentiated. Now di by dz is equal to minus of g plus j omega cv as we have obtained from the previous slide, and dv by dz is this value which is also obtained by the previous slide. If I substitute these two values here, then I get my next equations. D square v by dz square is equal to r plus j omega L into bracket g plus j omega c into v. Similarly, I get the equations for current. Now let us assume this multiplication of these two brackets as gamma square. So therefore I get my second order differential equations for transmission line as d square v by dz square is equal to gamma square v, and for current it is d square I by dz square is equal to gamma square by I. Therefore it is very clear that the transmission line, the equations for current and voltage for transmission lines, okay, they are similar. This gamma is now, gamma square is multiplication of these two brackets, so therefore gamma is equal to under root of multiplication of these two brackets. This, let's, r plus j omega L is nothing but the impedance of the series component, and g plus j omega c is the admittance of the parallel component. So if I substitute this value here, then I get gamma is equal to in the root of z, capital Z into capital Y. This gamma is a complex term, therefore it has some real value and the imaginary term. This alpha is called as attenuation constant, and it is a measure of amount of loss of power per unit length on the line. So as this wave propagates on the transmission line, some of the power is lost, and that is given by this alpha value. Similarly, j beta is called as phase constant, and it is the amount of phase shift per unit length. So as this wave propagates over the transmission line, the amount of phase shift which is present on the transmission line is denoted by this beta value. So this gamma is called as a propagation constant, and this alpha is called as attenuation constant. It determines the magnitude between the input and output quantities. That is, it basically tells you the attenuation that is produced as the wave passes in the network, and its unit is Nipper. Similarly, beta is phase constant. It determines the phase angle between input and output quantity, whether they are in phase or having some phase difference. And there is a phase shift which is introduced by network, which is given by this beta value, or there could be another way of saying that beta value gives you a time delay which the signal which undergone as it travels through the media, and the unit for beta is radians. So we have obtained this two equations, that is this equation, that is second order equation, d square v by dz square is equal to gamma square into v. If I think of solution of this second order equation, then the equation is of this form, that is v of z is equal to a e raised to gamma minus gamma z plus b e raised to plus gamma z. A and b are constant. So this term, first term, indicates a forward or incident wave from source to load, and the second term indicates a backward or reflected wave from load to source. We'll see the next part of the transmission line topic in the next video. Thank you.